There are a lot of ionic compounds, and many of them occur in the Earth's crust as minerals. They are also commonly present in the foods that we eat. They're generally very stable because the bonds that hold the ions together are very strong. These are just some examples. This is Morton's light salt, and what makes it light is that it's a mixture of sodium chloride and potassium chloride. So if you use the same amount of this salt, you'll get less sodium. Calcium carbonate. Calcium is a metal. Again, this is an ionic compound. That's the active ingredient in Tums. And here are two minerals, and they form really cool-looking crystal structures. So this is also calcium carbonate in a little bit different form than in Tums. I don't recommend, chomping on calcite if your stomach's upset. We're going to learn to write formulas for compounds and to name compounds. We'll start with the ionic compounds. When writing the formula, we start with the metal. Why? Because they decided to do it that way. Okay? There's a lot of things that are like that, right? So if you think about addressing a formal invitation, would you write Mr. and Mrs. or Mrs. and Mr.? Mr. and Mrs. Why? Because that's how people usually do it, right? Just because that was how it started, right? So the metal goes first. I think of metals as being masculine and the non-metals as being feminine, right? So they are different. So we've got the metal cation. Got the metal cation. We're going to write its symbol and its charge. And then we're going to write the non-metal with its charge. And then we have to figure out how many of each of them do we need. We're going to use subscripts so that overall our formula is neutral. And then you should always check. So let's, I guess it's not an example yet. So ionic compounds always contain positive and negative ions because positive and negative attract each other, right? So my analogy based on gender is based on like the Middle Ages or something, okay? There's male and female and those are attracted, and it's just that way because positive and negative attract each other. Two positives, that wasn't good for it. Two positives, this is electricity, electric charge, two positives do not attract each other. So no commentary on anything in society. It's an analogy that helps us to remember. So the first element is usually a metal. And the one exception that we will see in Chem 1A is ammonium ion. This is an ion composed of nonmetals, but it has a positive charge. Everything else that's ionic in Chem 1A will have a metal first. And I say in Chem 1A because outside of Chem 1A there's a whole bunch of other things, but we're not going to worry about those. So we need the sum of the positive charges and the sum of the negative charges to add up to 0, so we have a neutral compound. And the formula for ionic compounds is always going to be an empirical formula, the smallest whole number ratio. So let's practice this. So we're looking at the compound that forms between potassium and sulfur. We need the symbols for those elements. What's the symbol for potassium? K. And what's the symbol for sulfur? S. What charge does a potassium ion have? +1. How do we know that? It's in group 1. We learned that in chapter 2. What charge does a sulfur ion have? -2. So you can do group number -8, or you can start at the noble gases and count backwards. Chlorine is -1, sulfur is -2. So these have predictable charges. Now we have to figure out what arrangement of these together will make a neutral compound. And this is actually so simple that it's hard. And people make up this crisscross thing and they do all these other things. And I invite you to listen and try to just understand what I'm talking about here. So I need the total charge to be equal. And right now I've got a total of -2 and +1. Those are not going to add up to 0, right? So what I need is for this to be -2. Now, I need that to be +2, right? Well, how can I accomplish that? I can't change the charge on the ion, but I could recruit 2 ions. So we need 2 potassium ions for every sulfide ion so that it's neutral. So then we write K2S. Okay? We can make analogies with bowling balls or little boys and cookies, or there's all kinds of other things. And all of those people are like, well, of course, it's the same thing here. Okay, aluminum and nitrogen. What's the symbol for aluminum? Al. And which charge does an aluminum ion have? 3+. Because it's a main group element in group 3A, right? I make my lowercase l's kind of loopy like a cursive L to make sure that it doesn't get mistaken for a 1 or a capital I. So there's aluminum, and nitrogen is N, and what's the charge on nitrogen? -3, yeah. So here, they have the same magnitude of charge, just opposite in sign. So how many of them do we need to be neutral? We just need the 1 of each, right? So we can just shove those guys together. Actually, I can shove those guys together. Get over here, and now they're together, and together they make a neutral compound. Okay, any questions? There are common names for a lot of compounds. Water is a common name. It's not the systematic name, but all compounds do have systematic names. And so we are going to learn the basics of systematic naming. So the first thing we need to do is identify what kind of a compound it is. Because ionic compounds have one set of rules and molecular compounds have another set of rules. Because the different sets of rules work better for each. It's a little bit like naming conventions among humans in different countries and different cultures, right? My ancestors came from Sweden, and in Sweden, they don't do this anymore, but in Sweden, if your dad's name was John and you're a guy, then your last name is Johnson because you're the son of John. And if you're a girl, your last name's Johnsdotter. D-O-T-T-E-R, it even sounds like daughter, but Johnsdotter. Okay? Here in the United States, the typical thing is the children take the last name of the father. In some countries, people only have one name. They don't have 2 names. So we have different systems for different cultures, right? So we have different rules for different kinds of compounds. So we just need to recognize what type of compound we're looking at. So ionic compounds, again, usually because of that one exception, metals and nonmetals. And there's always 2 ions in Chem 1A, only 2 ions. So what we're doing is we're looking at the first element. Look at the first element, Na. Is it a metal? Yeah, ionic compound. Here, Al2. Al, is it a metal? Ionic compound. So this is the metal ion, the positive ion. Everything else is the anion. Okay, so we're not going to call this dialuminum carbon trioxide tri or something. Okay, we're not going to split all the ions up because these guys come as a group that's a polyatomic ion. What do the parentheses mean? It means there's 3 of what's inside the group, right? I realized yesterday that there's no real explanation of that in the slide, and I looked in the book, and they don't really mention it either. So, we need to make sure we point that out. I think of polyatomic ions, like carbonate here, as being a little like bundle-packed stuff that you get at Costco, right? So in the summer, they have this pack, and it's ketchup and mayo and mustard and relish, and they're all bundled together. And you say, but I just want the ketchup. No, you have to buy the whole package, right? It's shrink wrapped. You can't break it apart. If you do, they don't know what to do with it at the register. So the parentheses here are like the shrink wrap, okay? And on the outside is the number. That tells us how many of everything inside that we have, okay? And the alternative, you can see why that's necessary, Al2CO3. Well, how big is the space there? What does the 30, is it 33 oxygens? It doesn't work. So we need the parentheses. Okay. We only use parentheses if we have more than one polyatomic ion because you don't want to waste the shrink wrap, right? It's plastic, it's not good for the environment. So we're only going to use the parentheses when we need them. That's a brand new one too. These things just come out of my head. Anyway, back to what we were doing. So this guy, 4 different elements. Look at the first element. Is it a metal? Yes. Ionic compound. The metal is the first ion. Everything else is the anion. MgSO4, first element, metal. This is an ionic compound. The one exception is something like NH4Cl. So NH4, that's also ionic. Your book talks about the 2 different types of ionic compounds based on how many ions that the metal can form. So some metals only form one kind of ion, and those are the ones we've learned about, the ones in groups 1A, 2A, and 3A on the periodic table. The group 1A metals form +1. Group 2A is +2. Group 3A is +3. Because they lose some electrons so that they can have the electron structure of a noble gas. They want to look like the cool kids in high school, so they dress like them. The other elements, the other metals, can form multiple ions, like iron can be +2 or +3. And so then the naming has to be a little more descriptive. So these are the metals that only form one cation, right? So group 1A, group 2A, group 3A, and then zinc and silver also do that, even though they're in the transition elements. None of these rules can just be a rule, right? There's always has to be an exception. And then this guy over here, scandium, also just forms a single ion. We're not going to run into scandium much, so we're going to ignore him. We're going to think about group 1A, 2A, 3A, zinc, and silver. The names of these ions are the same as the element name. Isn't that nice? An iron ion, I'm sorry, not an iron, like a sodium ion is just sodium. Then there are others that form more than one. So here we have to have something in the name that tells us which one we're talking about. So looking at iron here, there's Fe2+ and Fe3+. So the current system, the good system, we're going to use Roman numerals. The older system, they changed the suffix, the ending of the name, and us meant the lower charge and ik meant the higher charge. So if you see anything like that, just go look them up. but you do not have to know these names. But we use Roman numerals. So humans use Roman numerals too in naming, right? Think of kings of England. There was a king named Henry. And then there was another king named Henry. And another one, and another one. How do we tell them apart? Roman numerals. Henry II, Henry III, Henry IV. We still do that if you, if the son has exactly the same name, first, middle, and last as his father, then we get senior and junior, but you do it one more time, and now you've got the second and the third, right? We only use Roman numerals when they're needed, right? So, one of my kids is Michael Kawagoa. Michael's an extremely common name. Kawagoa is like an extremely uncommon name. There is no one else in the world named Michael Kawagoa. So does he need a Roman numeral after his name? No, because there's only one of him, right? John Smith, well, do you mean John Smith Sr., John Smith the second, the third, the fourth, the 17th, right? We need to specify which one. So we're only going to use the Roman numeral when we need it. But the Roman numeral is really, really handy because it just tells us what the charge is. So iron 2 has a 2 charge. Iron 3 has a 3 charge. So the Roman numeral just flat out tells us what the charge is. Metals always have positive charges. I get a little carried away with that sometimes. Okay. Occasionally I make up slides like this. Mrs. K's tricks. So what we can do here is remember that groups 1A, 2A, 3A, zinc and silver, no Roman numeral, because they form only one kind of ion. Group 1A is +1, group 2A is +2, group 3A is +3. What about the zinc and silver business? Well, aluminum is +3, as are gallium and indium, but those don't show up very much. Zinc and silver also only form a single ion. And so if we think of this as going downstairs, or going up the stairs, aluminum is on the 3rd step, zinc is on the 2nd step, silver is on the 1st step. It just goes down 3, 2, 1. So groups 1A, 2A, 3A, zinc and silver, no Roman numeral. Any other metal, Roman numeral. And my goal is to say group 1A, 2A, 3A, zinc and silver enough times during lecture that you can't help but remember it. It's just groups 1A, 2A, 3A, zinc and silver. Okay, what about anions? So monoatomic anions, this means they have one atom. So it's just a single atom. And so the name of this, we take the element's name and we change the ending to "ide." And this fits in with my whole stereotypical marriage business with the men and the women. So man and woman got married, 200 years ago. What does the woman do with her name? She changes her last name to match her husband's name, right? A lot of people still do that, personal choice. So I think of the nonmetals as being feminine. So this is like the woman in the marriage. They're getting married when they make a compound. And so she changes the end of her name. She only has one name. She doesn't have a first and a last name. So she just changes the end of her name. So fluorine becomes fluoride. Chlorine becomes chloride. Bromine becomes bromide. The charges, we already learned, group number -1 or count backwards from the noble gases. Any questions? So in our ionic compounds in Chem 1A, there's going to be one metal, that's the cation, and one non-metal, one anion. It might be a polyatomic ion, or it could be a monatomic ion. So all of the ionic compounds that we're going to learn how to name are binary compounds meaning they have two elements. No, I take that back. Now, I don't edit videos. Binary ionic compounds, we'll just start again. Binary ionic compounds contain only two different elements. The other one, forget it. Anyway, so it's really pretty straightforward. We learned how to name cations, and we learned how to name these monatomic anions. And to name the compound, you write the metal's name first and the non-metal's name second, just like Mr. and Mrs., just because it was the way that people agreed to do it. It has to be positive and negative because of the charge. So if we look at KCl, potassium is in group 1A, so it doesn't need a Roman numeral. So the name of that ion is just potassium. And chlorine, as a monatomic ion, changes the ending of her name to chloride, and so we have potassium chloride. Here, CaO, the first element is calcium. We find calcium on the periodic table, group 2A. If it's in group 1A, 2A, 3A, zinc or silver, no Roman numeral. Just calcium, and oxygen becomes oxide. Okay? So let's name this compound. This is Ag3N. Well, the first element is the first name, and what's the name of that element? Silver. Whoops. Then we ask ourselves, is that in group 1A, 2A, 3A, zinc or silver? Yeah. Group 1A, 2A, 3A, zinc or silver. Yeah. It is. No Roman numeral. Okay, so we're done with that one. And then nitrogen, as an ion, becomes nitride. So we change the ending of the name, nitride. So you may think, well, why do you change the ending of the name? Why can't it just be nitrogen? Well, I don't know for sure, but what makes sense to me, and I like to make up reasons that make sense to me, is if you wrote silver nitrogen, it might be unclear as to whether you're intending to write a compound or you're just listing some elements, right? Silver nitride, the changing of that ending, tells me that this is part of an ionic compound. So we can do the other way around and write a formula. Here we have rubidium sulfide. What's the symbol for rubidium? Rb. What's the charge on rubidium? +1. We know that this is in group 1A, 2A, 3A, zinc or silver because there's no Roman numeral. And sometimes you have to look around a little bit because there's a lot of letters up there. And sulfur is S with a charge of -2. So these charges need to be equal. So currently we have -2 and +1. We need more of this guy. So we're going to just draw him in again. So there's 2 of those. Now it's +2. And they are the same. If this has been a problem for you in the past, figuring out these formulas, start out by literally drawing this out. And then once it clicks for you, you won't have to do that anymore. Because what we're looking for is the least common multiple of the charges. So if you're a math person, you'll go, oh, and the rest of you just forget that I said that. So I have 2 of these. So it's going to be Rb2, and I have 1 sulfur, so it's 1s. Any questions? If we have one of the other kinds of metals that forms different elements, the only difference in the name is that we have to include the Roman numeral from that element's ion name. If we have a formula and we're trying to identify the Roman numeral, we'll kind of have to do a little digging and figure out from the charge of the anion what the charge of the cation is. So here, we're going to name CrBr3. Well, what's Cr? Chromium. Is chromium a metal? Yes. Is it in groups 1A, 2A, 3A, zinc, or silver? No, it's not. We don't care where else it is. It's just not in there. That means it needs a Roman numeral. So I'm going to put the parentheses here, and I'm going to figure that out later. And then the other part here comes from bromine. So that has the ending changed to bromide. Okay? How do we figure out the charge? Well, we kind of have to do the opposite of finding the formula. And again, it can help initially to just draw things out. So I have one CR and I have 3 BRs, because that's what the formula tells me. Right? BR3. Okay, so I got 3 of these guys and one of those. And I know the charge on this from the periodic table. Each of these is -1. So my total negative charge then must be -3. Right? So if the negative is -3, then the positive needs to be +3. Right? So we're going to take this charge and spread it over all of the metal ions. There's only one. So that must be 3+. So the Roman numeral is 3. I forgot to give you the brief review of Roman numerals. We'll do that now. So these are not Roman numerals. I think those are called Arabic, but I'm not sure. Anyway, so the Roman numeral for 1 is a capital I. I always put the little serif thing on the top and the bottom so it doesn't look like a 1 or an L. For 2, it's 2 capital I's. For 3, it's 3 capital I's. And you might think, well, we'll just keep going, right? 4 is 4 capital I's. But this would get really unwieldy if you're like dealing with the number like 100, and it just wouldn't work. So 5 is V. Don't ask me. They did it, right? 5 is a capital V. So 4 is the number before 5. It's one number before 5. And so this is 1 before 5. 6 is one number after 5, and so this is VI. And 7 is 2 numbers after I, and so this is VII. And then they get into tens and hundreds, and all those things have all different letters, but this is as far as we have to go. Just up to 7 is good. Okay? Okay, let's name this compound FeS. Iron. Is it in groups 1A, 2A, 3A, zinc, or silver? No. Parentheses, holding space for the Roman numeral. As would be named. It's sulfur, and as an ion, it's sulfide. We have to figure out what the Roman numeral is. So I'm going to write the symbols for the ions. Here we have one of each. What's the charge on sulfide? 2-. There's one of each, so what's the charge on iron? 2+. Right? I have one of these and one of those. Their charges must be of the same magnitude, the same size, just opposite in sign. So then this is iron 2 sulfide. Write the formula for ruthenium 4 oxide. What's the symbol for ruthenium? What might be a good guess? Are you? What does the Roman numeral 4 tell me? The charge. So this is positive 4. This is ruthenium 4+. That's not how many of them are in the formula. It's the charge on the ion. Okay? And then oxide is oxygen, right? With what charge? 2-. So we have to figure out how to put these together in the lowest ratio, right? So, really basic way is just see, well, what do we have here? Well, I've got +4 and I've got -2. I need more negatives. So if I draw in another of the negative ion, now I'm -4 and it's neutral. So RuO2. The non-existent formula is ruthenium and oxygen and potassium. Are you okay? Get really silly with element symbols. One of my pet peeves is none of them have the letter J. My first name's Jody, so I can't spell my name with element symbols. It's not fair. You've probably heard about a crisscross method where you take the 4 and it becomes the subscript for the oxygen and the 2 becomes the subscript for the ruthenium. And the thing you always have to check on is it the lowest ratio? Because if you do that, you're going to end up with Ru2O4, and you have to simplify that. So I think this method is better. Polyatomic ions. These are named the same way, except for the anion name, we're going to use the name of the polyatomic ion. The names and formulas of polyatomic ions must be memorized. I mean, how did we know that sulfur was S? We memorized it, right? And how do we know that oxygen is O? We memorized it. That didn't seem so much like memorizing. Memorizing all those polyatomic ions with their crazy numbers and charges, that seems a little harder. But that's just how you do it. So here are some common polyatomic ions. Acetate, carbonate. So this one is very similar to that one, right? The difference is it has an H and the charge is one less. And that's because here a hydrogen ion has been added. And so that was carbonate, and this is called hydrogen carbonate because it has a hydrogen ion in it. Down here we have phosphate, hydrogen phosphate, and dihydrogen phosphate. Hydrogen phosphate has one hydrogen. Dihydrogen phosphate has two hydrogens. Hydrogens have +1 charges, and so they affect the charge on the overall ion. Couple weird ones, cyanide is Cn-. Peroxide, this is just oxygen, but it has a charge and there's 2 atoms, so it is a polyatomic ion. And then hydroxide is a very, very common one. And our little positive friend down here, ammonium. Most of the polyatomic ions are oxyanions. Let's just go back there real quick. See how most of these have oxygen in them? Like, well, that one doesn't, and this one doesn't, everybody else does, right? So that's like super common. Those are called oxyanions because they have oxygen in them. And so the oxyanion names come from the name of the other element that's in there, and then suffixes and prefixes. And so the ending, the suffix can be ate or ite, and then there's some prefixes also. So NO3- is nitrate, NO2- is nitrite. The way I remember that is that nitrite is the light version of nitrate. It has a third fewer oxygens, just like Bud Light has a third fewer calories than regular Bud, right? So it's Bud Light, it's nitrite. Sulfite has one less oxygen. The number of sulfurs, the charge is the same. The only thing that's different is the number of oxygens. So sometimes there's more than two. So here we have chlorate and chlorite. But there's another one with one less oxygen than chlorite, and then there's this guy with one more than chlorate. So instead of having more different endings, we put a prefix on those. So perchlorate, per meaning more, like hyper, right? Hyperactive is more active. So perchlorate is more oxygen than chlorate. Hypo means less or below. Hypochlorite has less than chlorite. Bromine forms the same kinds of oxyanions, and the naming is the same. On that chart, that list of polyatomic ions, these guys aren't on there. We don't need them to be because they follow exactly the same pattern as chlorine. The chlorine ones are on there. And another sister of chlorine and bromine in that group, that family, is iodine. And so iodine also follows the same pattern. We have IO4 minus, IO3 minus, IO2 minus, and IO minus. So what's the name of this one, IO3? Iodate. So it's from iodine, that's iodate. One less oxygen, that's the light version. Iodite. One less oxygen, now we're below that, hypo, like a hypodermic needle goes below your dermis, below your skin. Hypoiodite. And this guy has an extra oxygen, right? So this is, we leave the high part, but per, from hyper, per iodate. So if you can remember that per means more, ite is the light version, and hypo means less than that, and you just memorize chlorate, you can do all of these. So another, this is Kay's tricks. Memorize the eights and the pattern. So hyper has one more, you memorize the 8, you've got the light version, and below is hypo. And just in case you're actually reading your book, this is upside down of how it shows in the text, because I think more should be at the top and less should be at the bottom. Same thing though. Only the number of oxygen atoms change. Okay, well, let's practice these. Name the compound SnClO3 2. Well, what's the first element? Tin. That's a metal. Is tin in group 1A, 2A, 3A, zinc, or silver? No. Needs a Roman numeral. What's the name of this guy? Chlorate. And how do you know that? Because you memorize it. So what you should do as you're doing homework, and we're going to be doing some nomenclature on the worksheet on Thursday, is try to come up with the name without looking it up. And then look it up and check that you got it right. If you just look it up every time, you're never going to really remember them. So with chlorine and oxygen, I mean, the two best guesses would be chlorate or chlorite. Some have hyper or per and hypo. Chlorine is one of those, but like with nitrogen, it's just the two. nitrate and nitrite. So, give it a good guess, and then check your answer. So this is chlorate. So this is tin something chlorate. Well, how many chlorate ions are in this compound? 2. And how many tin ions? 1. So this gives me a total of -2. I need a total of +2 on my cations. So this must be 2+. So tin 2 chlorate. Let's write the formula for cobalt 2 phosphate. What's the symbol for cobalt 2? CO 2+. Make sure that's a lowercase o, because an uppercase O would be oxygen. Phosphate. PO4 3-. And we should be able to guess PO something with some sort of negative charge, right? So just take your best guess and then check yourself. Okay, so we need to get these so they're going to match up. So I've got a total of -3 and +2. So I need more positives. So I'm going to put in another positive. So now I've got +4. Now I need more negatives. So that gives me -6. And now I'm short on the positives again, and you're like, oh man, we're going to go around and around. In lab, you can ask me, and I'll tell you the story about my grandma and bread and with it, but not right now. So let's just put another cobalt on here. Oh, okay, phew. We got there. There's 3 cobalts and 2 phosphates. Because 6 is the least common multiple of 2 and 3. Right? So we would write this as CO2. Phosphate is a polyatomic ion, and there's more than one of it. So we need parentheses around it. PO4, 2. Nomenclature, again, is like learning a board game or a card game. There's rules, and as you do problems, you name things, you write formulas, and you use the rules, and you're like, oops, nope, that was wrong. And you correct yourself, then the rules begin to make sense to you. And then it's not hard. Okay, we have 2 slides left. Kind of weird ionic compounds, hydrates. So some compounds have a specific number of water molecules associated with each formula unit in the crystal. So this is the hydrate, and this is the anhydrate, or the anhydrous form. Hydrate, you want to be hydrated, right? You need to drink enough water so that your body has enough water in it. Hydrate contains water. Anhydrous or anhydrate, the prefix an means without, so this does not have water. Here we can see their formulas. These are both cobalt 2 chloride. But this one, in its crystal, there are 6 water molecules for every 1 formula unit. And that causes the color to be different. Some other properties will be different as well. Most hydrates, if you heat them, you can drive the water off and get the anhydrous version. You can't just add a little water to this and go back. So we need to be able to name these. Have you heard of Epsom salts? Sometimes got a sprained ankle or something, your grandma says, soak your foot in Epsom salts, right? You draw out the water. Epsom salts is magnesium sulfate heptahydrate. It's a hydrate. So it's got the regular formula for the ionic compound, and then a dot and then the number of water molecules. This dot does not mean multiplication. It just means that those two are together. It's not just that I wrote 7H2O after it. So we use prefixes to indicate how many of the water molecules there are, because that's the only way we can tell from the name. So hemi is half, like a hemisphere is half of a sphere. Mono is 1, di is 2, tri is 3, think triangle, tetra, penta, pentagon has 5 sides, right? So these are common prefixes that are used in other places as well. So let's name these guys. First you name the ionic compound. So this would be what? Calcium sulfate. Calcium's in group 2, doesn't need a Roman numeral. What prefix do I use for half? Hemi. Hemi hydrate. What about this guy? What's the name of the first part? Barium. It's tempting to say dichloride, right? These prefixes are so nice, and we get to the molecular compounds, and we're going to use them, but we don't want to use them unless we need them, because that would make all of the names longer, and nobody wants that, okay? We don't need the prefixes for the ionic compounds because the charges tell us how many. So it's just barium chloride. We do need a prefix for the H2O because there's no way to figure that out unless they tell you, because some of these have different hydrates. There might be one that has 2 water molecules, and one that has 4, and one that has 8. So we use the prefix for 6. 6 and hexa both have X's in them. So this is hexahydrate. We should also be able to write the formula from the name. So copper 2 sulfate, copper 2, copper 2 plus. The Roman numeral is the charge. And sulfate, cheat and peek up here, sulfate is SO4, and it has a 2 negative charge. Those have equal magnitude, so we just need one of each of those. So Cu, SO4, dot, penta means 5, hydrate means water, 5H2O. The hydrate thing is not a big deal, but it is going to show up on a worksheet. More than one, actually.